Good evening, all of you. I am Professor N.N. Wagule from Bhagwan Mahavidyalaya Asti District Bid, presenting a paper on study on structural properties of CO cobalt ferrite substituted by manganese and Mn and zinc plus BA3 composites. Initially, I will very much thankful to Professor H.G. Kulkarni sir and Wellington College, Sangli for giving me opportunity to present my paper on the topic study of structural properties of COMNZ and Fe1.6O4 plus BaTiO3 composites. Outline of my presentation: introduction, experimental procedure, characterization of ME composite, results and discussion, and conclusion. Introduction. We know that the ME composites means what? What is the ME effect? Materials with ferromagnetic and ferroelectric are significantly important for many technical applications. And magnetoelectric effect is nothing but the effect which is produced by electric polarization of material by application of magnetic field, and vice versa, means if I applied a magnetic field on this material, then there is a electric polarization. When magnetic field is applied on the composite material, piezoelectric perovskite material and spinel structure of the ferrite phase particulate changes their shapes and they produce the magnetization, and due to the magnetization the strain is passed in the piezoelectric particles which results into the electric polarization. This is called as a magnetoelectric effect. So these magnetoelectric effect materials are technically very important. In many technical applications, these ferroelectric composite materials are used, which consist of ferroelectric materials and ferrite materials in definite proportion. And to get the better ME effect, the coefficient magnetoelectric coefficient of ferrite phase and piezoelectric effect of ferroelectric phase must be high, and that depends on structural properties of the material. So that's why in this paper I have selected manganese and Mn and zinc substitute manganese and zinc magnesium and zinc substituted cobalt ferrite and very familiar piezoelectric material, that is barium titanate. So from the study of ME effect of these composite materials from the literature survey, I noticed that for getting a large ME effect for the sensation or waveguides, that ME composite material should have large piezoelectric coefficient for ferroelectric phase and magnetization coefficient for ferrite phase. And also this large ME effect also depends on the resistivity of the materials. So to get the more large ME effect, the resistivity of material should be increased. So that resistivity of ferrometal depends on the sintering temperature, its crystal structure and porosity. So in this paper I have synthesized the ME composite materials in which the Mn and zinc substituted cobalt ferrites and barium titanate ferroelectric phase I have selected for my study. And to understand this resistivity property or magnetization property of this ferrite phase and as well as electric polarization property of barium titanate, I have to study their crystal structure. And to study the crystal structure, initially I have taken the XRD of these materials, and from the XRD of materials, various properties that I have studied, I have investigated their crystal structure and what are the properties of that crystal structure, and how I have increased the resistivity and magnetization coefficient of this cobalt ferrite, because cobalt ferrite is the best candidate which has high saturation magnetization then high magnetic moment, and to increase its resistivity, I have deposited zinc as well as manganese. Manganese substitution increases the magnetization, while zinc enhances the resistivity of the ferrite materials. And this barium titanate is a very good candidate for the piezoelectric materials, which have easily get polarized by the application of magnetic electric field. So, in my experimental procedure, I have synthesized Mn and Zn substituted cobalt ferrite plus barium titanate, and they are synthesized from the oxides of the constituent materials: cobalt oxide, manganese oxide, manganese dioxide, zinc oxide, and ferric oxide. I have taken in molar proportion, and they are sintered for 1100 degrees Celsius for 10 hours. And then I have get the ferrite phase, that is manganese and zinc substituted cobalt ferrite. And barium titanate, which is also I have obtained from the analytically grade barium carbonate and titanium oxide. I have taken in the molar proportion, and they are sintered for 1000 degrees Celsius for 8 hours, and the reaction takes place like this. In this barium carbonate and titanium oxide, when there is a decomposition reaction takes place, barium titanate is formed and carbon dioxide is released. So, after preparation of these Mn and Zn substituted cobalt ferrite and barium titanate, I have mixed these ferrites and ferroelectric phase in the definite proportion by taking the formula here COX COMn Zn Fe 1.604 plus 1 minus X B8AI3, where X varies from 0 to 1. This mixed powders, and then I have initially pressed with the help of a hydraulic press die to form a pallet of 2.5 to 3 mm thickness and having diameter 10 mm. After preparation of these composite materials, initially then I have taken XRD of these constituent materials. You will see here, these are the XRD of these constituent materials. Here we will see here when I have taken the XRDs of individual and composite material. These are the XRDs of composite materials. Here we have seen that these peaks which are observed in this XRD of this composite material clearly shows that the peaks corresponding to, say, suppose which are the peaks are there 220, then after 311, and then 222, then after 400. These are the peaks corresponding to the cubic spinel structure of the ferrite phase, whereas 100, 110, 111, 200, these are the peaks corresponding to the ferroelectric phase. And you will see here, these are X is equal to 0 means here these are the XRD pattern of ferroelectric barium titanate, and these are the XRD peaks of these composite materials. And here you will see there, if this composition of ferrite phase, that is X, goes on increasing from 0 to 0.25, 0.50 or 0.75, as it increases, then you will see here the peaks of ferrite phase, that is a cobalt zinc manganese zinc substituted cobalt ferrite increases, and the intensity of highest peak of barium titanate, that is say 110, that goes on decreasing. So from that I have calculated from this XRD pattern of the materials, I have calculated the percentage of the constituent phases in the substance. You will see here the ferrite phase percentage in the composite materials can be determined by the intensity of highest peak of ferrite phase divided by intensity of highest peak in ferroelectric phase in XRD pattern multiplied by 100. Using this formula, I have calculated the percentage of constituent phases in the composite, and that is listed in next table. Then it is observed that as the ferrite phase percentage observed calculated from the intensity peaks, and I have taken in the composition perfectly matches. And then I have calculated the lattice constants of ferrite ferroelectric phases and their composites using the formula, that is A is equal to, that is lattice constant is equal to D into under root n, where D is the inter lattice spacing, and n is nothing but the n is equal to h square plus k square plus l square, where h, k, l are the Miller indices, and interplanar spacing D is given by D is equal to n lambda upon 2 sin theta, where lambda is the wavelength of X rays used for the taking XRD, and theta is the angle of diffraction. And n is equal to h square plus k square plus l square. This is the n for the ferrite phase, which is the cubic structure, and for the cubic structure we have to take n is equal to h square plus k square plus l square, here h, k, l the Miller indices. And for calculating the n for ferroelectric phase, we have to take it as their Miller indices I have indexed in the graph paper here. These are the Miller indices here, and taking these are the Miller indices of the ferroelectric phases. For suppose say angle near about say 30 degree, the peaks have the Miller indices 110, means h is equal to 1, k is equal to 1, and l is equal to 0. So taking these values, I have also calculated n for the ferroelectric phase, that is h square plus k square plus l square into a square divided by c square. By using this formula, I have to calculate the Miller and lattice constants of the ferroelectric phases also. And after calculation of these phases in the ferroelectric phases, then I have noticed that they have listed in this table, as ferrite content X increases, the lattice constants of the ferrite goes on increasing. Initially x is equal to 0 means ferrite phase is totally absent, and only there is ferroelectric phase. So ferroelectric phase has two lattice constant A and C, because it is a perovskite structure. That's why it has lattice constant A and C, and A has value 3.978 and C has value 4.040. And when ferrite content X increases in the ferroelectric phases, that is X becomes 0.25. At that time, these are the ferrite phase has lattice constant 8.35 angstrom, while the ferroelectric phases have lattice constant 3.968 and 4.031. So you will see here from the XRD pattern that as ferrite content X in the composite goes on increasing, the lattice constant of ferrite phase goes on increasing. That's while the lattice constants of ferroelectric phase goes on decreasing manner. Okay, and then also next in the next step also I have calculated the X-ray density and theoretical and experimental X-ray density. So what is X-ray density? While calculating, initially I have calculated the experimental density. That experimental density is calculated by the relation rho 3 is equal to m1 plus m2 divided by m1 into rho 1 plus m2 into rho 2, where m1 and m2 are molar weights of ferrite and ferroelectric phase respectively, while rho 1, rho 2 and rho th are the theoretical densities of ferrite, ferroelectric and Me composites. And by these density of these composite materials I have calculated by the Archimedes principle, using the Archimedes principle. What is Archimedes principle? That every substance when dipped in the liquid, it displaces that liquid equal to its mass. So that using that Archimedes principle, I have because density equal to mass upon volume, so I have calculated the theoretical densities for this composite material using this formula. and that's how I have listed in the next table. These are the theoretical densities here. As these are the theoretical densities of the materials. For x is equal to 0, 4.35 gram per centimeter cube. For x is equal to 0.25, it is 4.41. For x is equal to 50, it is 4.55, and so on. You will see that as ferrite content x increases, the experimental density that goes on increasing. And for the ferroelectric phase also, this experimental theoretical density, when we have calculated using the XRD pattern. So how we can calculate the X-ray density? So to calculate the X-ray density, I have used this formula, that is X-ray dx is equal to 1 minus x into me upon NaFe into C plus x into 8 mf divided by NaF cube. Where what is the mf? Mf is a molecular weight of ferrite phase, and what is the AF and AFC? AF is the lattice constant for ferrite, and AFC is the lattice constant for ferroelectric phase. And what is Fe? Molecular weight of the ferroelectric phase. And what is MF? MF is the molecular weight of the ferrite phase. And as in the, it is a cubic structure for ferrite phase, we have to take the 8 MF, because 8 molecules, 8 number of molecules per unit volume of the cubic cells are present. That's why I have taken the 8 MF. And from this formula, when I have calculated the X-ray density, that is listed in the table, next table, that is here. These are the theoretical densities of these composites and ferrite and ferroelectric. For x is equal to 0, that means ferrite, the theoretical density calculated by using above formula 4.21, and then for x is equal to 0, that is 4.23. For x is equal to 0.50, it becomes 4.39 gram per centimeter cube, and so on. So these are the theoretical densities and X-ray densities of the ferrite, ferroelectric and their composite material. That's why I have listed in this table. And and after calculating these X-ray densities, I have also calculated the porosities, and the porosity of the material is given by percentage porosity is equal to 1 minus dB upon dx. What is dB? dB is nothing but the macroscopic density obtained from the Archimedes principle. And what is dx? That it is the X-ray density which is obtained from the XRD pattern of the materials. And P is nothing but the percentage porosity, and this porosity is play a vital roles in the resistivity of the composite materials, which in turn play a very important role to increase the magnetoelectric effect, because for to get more magnetoelectric effect, substance should have large resistivity or enhanced resistivity. So from this study, I have comes to conclusion that composites of ferrite, ferroelectric, that is Mn, Zn substituted cobalt, ferrite and barium are successfully synthesized using the ceramic technique. Structural parameters such as the lattice constant, X-ray density, bulk density, that is dB, of the ferrite, ferroelectric and their composites are reasonably matched with the standard data. Lattice constant A, that of the ferrite phase, increases from 8.37 to 8.44 due to the addition of manganese ion in the cobalt ferrite, and that obeys the Vigard's law. The high value of porosity of present composites may be due to the sintering of the composite materials at elevated temperature. Means at this time of synthesis I have used the temperature 1000 degrees Celsius, but after making the composites, that is pellet, I have sintered at 1150 degrees Celsius, and that due to the elevated temperature, their porosity increases, and the presence of this Zn ion in the cobalt phase, ferrite phase, that increases the resistivity of the material. So these are the materials are very good candidates for enhancing the resistivity, and in turns they will increase the magnetoelectric effect, and that enhanced magnetoelectric effect I have reported in my next paper. Thank you.